This is also a problem about a monatomic gas, and it says the work done by 1 mole of a monatomic ideal gas, gamma equals 5/3, and expanding adiabatically is 825 joules. The initial temperature and volume of the gas are 393 kelvins and 0.100 cubic meters. Obtain A, the final temperature, and B, the final volume of the gas. First of all, the only reason that they tell us it's a monatomic gas is because they derived in the book the adiabatic index gamma equals 5/3 only for monatomic gases, and for diatomic gases such as O2 or H2 or N2, so nitrogen, oxygen, hydrogen, they didn't develop them, but they would have to give us a different one of 7/5, which then is 1.4. And here for monatomic ones such as helium, krypton, xenon, so all the noble gases, they would give us 5/3, 1.67. And if we had like triatomic gases like CO2 and H2O vapor, we would have to be given 8/6. Depends on the problem, but for the most part, that's the reason why they give us the monatomic gas, because they have already derived that gamma for us. So here again, I chose the same drawing that was supplied in the software, and that would be an expansion here, and in this case it would be an adiabatic expansion, and then actually there is no heat exchange, so when they put red on here, that shouldn't happen. So it's kind of, it's not representative of what we have here, but that's the closest I could come up with some kind of expansion. It's an adiabatic expansion, and let's see what I'm going to do here. So I need more space. Okay, so the PV diagram looks kind of like this. PV, and then we start somewhere here, and it's an expansion, so it goes to the right, and then the pressure is supposed to go down, so we're gonna have this one here, this kind of curve, and then it ends up here, and then the area underneath, that's the work done, and they give that to us. So let's see, the work done is 825 joules, so they give that to us. The heat is applied because it's adiabatic. There is no heat flow, so that comes out to 0. And because this one is 0, then delta U indeed equals negative the work. So when 825 joules are done by the gas, then that means that the internal energy has to go down by 825 joules. So this one is done as well. Then let's see, they tell us what the initial temperature is. So I think I'm going to write Ti. Yep, I'm going to write Ti, that is given. They tell us what the initial volume is, so that one is given, and then they ask us what is the final temperature and what is the final volume of the gas. So final temperature and final volume. First of all, I'm going to look again at the PV diagram. So here we start out with some kind of pressure, then we end and volume, then we end up here with a smaller pressure and larger volume. And what happened to the temperature is during an adiabatic expansion, with the internal energy going down, I said earlier that's the negative of the 825 joules of work that were done. Therefore, the temperature has to go down. So during an adiabatic expansion, the temperature decreases. So our final temperature needs to be smaller than our initial temperature, and obviously our final volume has to be larger than the initial volume. They ask us first to figure out what the final temperature is, because when you peruse the equations that are given in this chapter, first of all, we can only use the ones that have the word adiabatic in front of it, or the ideal gas law. that applies to everything, but for example, we cannot use an equation that specifically says this is only for an isobaric process or this is only for an isothermal process. We have to use the ones that either say adiabatic process or it's not specified, as I said, such as the ideal gas law that always applies. So one of the equations here actually says that the work equals 3/2 times the number of moles times the ideal gas constant, and then parentheses the initial temperature minus the final temperature. And I wrote down the correct equation, and you may have already seen what I overlooked earlier. The number of moles indeed is given. They tell us it's 1 mole, and when I wrote down the variables in my table here, I spaced that it's actually given as 1 mole, and notice that everything in here is given, and that means that this is actually for part A, that the final temperature equals work divided by 3/2 nR minus Ti when I get that to the other side. So I divide by all of this here, the work, and then I subtract the initial temperature, but then I still have a negative in front of the Tf, get that negative to the other side, so that one here changes then to a positive, and then one changes to a negative. So all we have to do is plug in the numbers. So we have negative 825 joules divided by 3/2, 1 mole, and 8.314 is the ideal gas constant. Top of my head, actually. I kind of have that memorized. 8.31 for the ideal gas constant, and then add to that the original 393 kelvins, and you come up with some number, of course positive because we're in kelvins, so some positive number in kelvins, around 320 kelvins. Okay, for part B I need a lot more space. So part B, what we're going to do there, we have to figure out what the final volume is. When you look at the equations for an adiabatic process, we need the pressure because they give us this equation, Pi Vi to the gamma, and of course the gamma is 5/3. They tell us that. I could also write this down here. So gamma is given. And that equals Pf Vf gamma